The largest black hole in the universe has a problem. We have never actually weighed it. For years, one number has done the rounds: 100 billion times the mass of the Sun. A single object that could swallow our entire solar system many times over. It has a name, Phoenix A star, and it sits almost 6 billion light-years away, buried inside the most X-ray-luminous galaxy cluster known. But that number was never measured. It was modeled, estimated, inferred, and the astronomer who helped reveal this object to the world later went back with better data, and a very different picture emerged. Phoenix may contain the largest black hole ever proposed, or it may be a legend built from the way we tried to measure the invisible. To understand the problem, you have to know how this object was found and how the famous number was built. In 2010, a telescope stood frozen at the South Pole. It was not looking for stars. It was looking for shadows. When the oldest light in the universe, the afterglow of the Big Bang, passes through a massive cluster of galaxies, the cluster leaves a cold imprint in that light. The South Pole Telescope found 26 of these imprints. One was unlike anything astronomers had ever seen. 2 years later, in August 2012, a young astronomer at MIT named Michael McDonald stood up at a NASA press conference and told the room what that imprint was. A cluster of 1,000 galaxies, almost 6 billion light-years away, forming new stars at 740 a year. Our entire Milky Way produces one. By every rule astronomers knew, the central galaxy of a cluster like this should be dead. McDonald had found the one that was alive. They named it Phoenix. Buried at its center was the object that would become the most famous giant in modern astronomy. The 100 billion figure did not come from weighing the black hole directly. Researchers modeled the power of the cluster's central engine, simulated how that growth would reshape the stars packed around it, and under the most extreme conditions, the model suggested a black hole of order 100 billion suns. It was a serious inference built from real observations, but every layer carried an assumption: how efficiently matter became energy, how long the black hole had been feeding, how the stellar core responded. The headlines survived. The assumptions mostly disappeared. In 2019, McDonald went back to Phoenix with sharper eyes, Chandra in X-rays, Hubble in visible light, the Very Large Array in radio. And the picture he and his colleagues built was not of an overgrown monster. The cluster's gas was cooling at extraordinary speed. The black hole was launching powerful jets, but its feedback was not fully stopping the collapse. McDonald would later compare a galaxy cluster to a cup of coffee. Even a 10 million degree cup of coffee, he said, is going to cool. Phoenix was the first cup anyone had ever caught cooling. Under this picture, Phoenix might not contain an overmassive giant at all. Its black hole could be undermassive for its environment, still catching up toward 10 billion suns. Same cluster, opposite histories, no direct weight. So how do you weigh a darkness you cannot resolve? Nearby, the cleanest answer is motion. At the center of our own galaxy, astronomers watched a single blue star, called S2, complete a 16-year orbit around Sagittarius A star. The curve of that orbit revealed 4.3 million suns packed into a region no larger than our solar system. The work earned a Nobel Prize in 2020. Motion drew the scale, but Phoenix is almost 6 billion light-years away. We cannot isolate a single star near its center. The local gold standard simply disappears. At that distance, astronomers must build scales from indirect evidence, gas velocity, emission lines, and the way gravity bends background light. That last method changed the investigation. In 2025, a result from the cosmic Horseshoe finally delivered the kind of giant this story needed. 5 billion light-years away, a massive foreground galaxy bends the light of another galaxy behind it into a near-complete ring. Near the center is a smaller radial arc, passing so close to the hidden black hole that its shape carries the black hole's gravitational fingerprint. Researchers combined Hubble images of that arc with two-dimensional measurements of how stars move through the foreground galaxy. Lensing and stellar dynamics modeled together. The result? An ultra-massive black hole near 36 billion suns detected at high confidence with an uncertainty of roughly a third. Not Phoenix, not TON 618, a black hole most people had never heard of, revealed because one galaxy bent another galaxy's light across exactly the right path. Once one number is measured this carefully, the old leaderboard starts to dissolve. Consider the previous champion. In 1957, at an observatory in Mexico called Tonantzintla, a small telescope was photographing the constellation of the hunting dogs. On one photographic plate, a faint blue dot appeared. The astronomers cataloged it as object number 618. They thought it was a star. It was not a star. The light they had captured had begun its journey 10.4 billion years ago, long before Earth existed. It was a quasar, a black hole surrounded by superheated gas, screaming with energy as it spiraled inward. They called it TON 618. It became one of the most famous candidates for the largest black hole humanity had ever found, somewhere between 40 and 66 billion suns, depending on which analysis you trust. Phoenix has a spectacular model-derived estimate near 100 billion suns, and no direct dynamical measurement at all. The one figure we can actually defend, 36 billion, belongs to an object that was never even in the contest. Then theory adds another warning. In 2016, the astrophysicist Andrew King asked how big a black hole could possibly grow by feeding. His answer was roughly 50 billion suns. Beyond that mass, the glowing disk of matter spiraling inward would become so heavy that its own gravity would tear it apart, fragmenting before it could feed the black hole in the usual way. The luminous engine stalls. Let the black hole spin fast enough, in just the right direction, and that limit lifts toward 270 billion. But even this is not a hard ceiling on mass. A black hole could keep growing through mergers in the dark without ever lighting up. Theorists later gave a name to the class of objects that might live beyond these limits: stupendously large black holes. The universe, apparently, dares us to find one. Phoenix may exist at that scale. Right now, the evidence does not force us to believe it. So what is the largest black hole in the universe? The truthful answer is that we do not know. We have famous candidates with spectacular numbers. We also have a smaller group whose masses are anchored more tightly to motion and gravitational lensing. At roughly 36 billion suns, the cosmic horseshoe black hole is one of the strongest, ultra-massive measurements yet. Phoenix may still be larger. In 2025, the James Webb Telescope traced extraordinary cooling gas flowing toward the central galaxy, raw material for hundreds of new stars a year. Phoenix is still changing. Gas is still cooling through the cluster and feeding an extraordinary burst of new stars. But Webb did not weigh the black hole. Look again at that faint smudge of light we started with. It has not changed. What changed was the confidence we placed in one number. The real story of the largest black hole was never its size. It is the slow, stubborn work of weighing things we will never be allowed to touch, and being honest about the gap between what we have measured and what we only wished were true. The biggest number is not the same as the biggest fact, and for now, the universe is keeping the difference to itself.